So everybody, we have a very special discussion here. Something beautiful happened. We have published a new paper, and all of the co-authors are in this call. And it's a very special paper because it's on a topic that is very interesting, and it evokes a lot of discussion. And this paper is therefore, I think, at the right timing. It touches upon some important points. What is the topic? Validation of CFD models. So computational fluid dynamics and CFD, are we losing the balance? And to put it in a little framework, some introduction, we have Daria Sudrawska, who is at the bottom of the screen. She started her internship at AM Team, did a lot of literature research on validation of CFD. We started discussing with the colleagues of Biomed Ghent University, so Professor Ingmar Nopens, his team. And then we found out, well, this is a great discussion. It was submitted to the Water Matex conference, IWA, so International Water Association Conference, Water Matex. We presented the results there in a very interesting presentation, I think. But then, of course, it got a lot of value, and finally, is this going to be published in Water Science and Technology? So it's Daria's first peer-reviewed publication, and actually it's Nopens et al. So Ingmar Nopens is the first author, and that is a long time ago, right? How long is that ago?
Oh, that's a good question. I would need to check. It's probably, must be 5 years or something. I think the last one was on population balance models. I think it was from a WWT mod in 2014 in Spa. Also water science technology paper. So I think that's fairly similar.
Okay, yeah, that's good. First author. Congratulations with that. Of course, we have a mixture here of, let's call it, industry people and academics. So doing research versus application of CFD models. But we managed to come together and develop a common vision in this paper. So I am very, very interested in hearing your vision about your personal vision and your personal touching points with validation of CFD models. And I will start with Usman, who actually devoted a whole bunch of his professional career to computational fluid dynamics. So what is your what is validation for you, Usman, and how is it important in your life?
Yeah, well, validation is really, as it says, validation. It really validates not only the model, but also yourself, like all the assumptions or all the things you foresee in a certain project or in a certain system. They get validated by the help of validation, which is actually the comparison between measurements and your modeling outputs. So it has been quite a significant part of my life since I started doing CFD modeling. With CFD, it is very important actually to have the confidence in the models, and the only way we find, so there are two actually ways where you can actually suggest that your CFD model is good. One is that you get an outcome which is in line with this reality. So which means that if you are improving a certain performance of a system, you see that the model also predicts that, and in reality it's also happening. So that's also a validation or confidence building in your system. But then another way is that you artificially actually measure at a certain locations or certain things or certain parameters which you normally don't do, but you just do it to compare it with your model, and then you compare the outcomes and see if the both things are comparable or not. And that is a very strong validation of the model. Both of these things are very important, and what I found, depends on really the objective of your study or of your system. You can choose between one of them. But of course, I personally feel the measurements and going in depth is more robust. It's more generates much more confidence in the model and makes the model widely applicable to a variety of applications. Whereas if it's really one system, you are looking at the performance of the system and comparing the performance of the model, then it can be a bit more case specific, or the system-specific validation. And then whenever you have to do another application, you have to recalibrate or revalidate the model. So overall, yeah, I love it. Not because we have been successful multiple times, but also because it just gives you this extra confidence in your own work, which you're doing, is really valuable, and that just adds a huge lot of value into the model. Yeah.
So Ingmar, I will go to you now. So you're the first author of this paper, and you have, of course, have done a lot of work in setting the framework here. What is the take-home message of this paper?
Well, I think there's probably several. It's not just one. I think I can join Usman in stating that validation is an important aspect. But I think what we also shown in the paper is that indeed your objective can be quite different. I think if you really look at it in a purely scientific setting, you would want to dig deep and get things as close as possible. But obviously, we always have to bear in mind that we will never build the perfect model. So you will always have some uncertainty remaining, and of course, that is typically what you want to do in a scientific setting. Which is quite different, I think, if you look at it from an application perspective. And I think it's also important that this, I would say, this question or that the comment that you always get for, the validation is maybe not up to the level that you would want, should not, in my opinion, interfere with starting to apply these models. Otherwise, you will just lose out on opportunities because the thing is that even if you would use a CFD model that is not validated up to a certain level, doesn't mean that it is useless, and it might be better than any technique that you have been using up to now to, for example, design a system or optimize a system. I think another take home is that there's a vast difference between the scale of a system that you're looking at. I think we demonstrated a mixing vessel in a lab scale environment up to I don't recall the exact number, but up to hectares of a basin. And still, I think that maybe it's not the exact digits behind a comma that are correctly predicted, but at least you see that there's that it makes sense, that there is a lot of value in those models. So, and that's why I think in the title we refer a little bit to that balance. Like, should we go completely and only start using models in practice when they are completely validated? I think that is would just miss out on some things. And I think the evolution or the development of CFD at this moment in time is gaining so much pace that it would basically the industry also starts noticing the value of it, and it would be stupid to then miss out on that chance and say, oh yeah, hold on, we have to still validate for another year before we can actually give you an answer. That's not how things work. I mean, maybe allow me, it has nothing to do with CFD, but we are actually right now suffering exactly the same discussion with epidemiological models that are now used to predict corona. There are a lot of scientists that say, oh yeah, first we have to wait for validation before we can actually use the models and do something about how to get out of the lockdown. That doesn't make sense. And I think it's a very nice example of, again, a really scientific, solid scientific approach versus a really applied approach. Right? So, yeah, in a nutshell, and I think you can, yeah, basically, it's an analogy that is crystal clear to me. So, and I also evolved over time, and being really a scientist, yeah, you want to get that, and I see that really as something that researchers should still be pushing forward. But on the other hand, I think the application side should not wait until all the stuff has been validated, because there's so many things that are hampering. At this point, the real hampering thing is the measurement methods. That is really the hampering part. It's not the CFD, because with the CFD you can do all kinds of things. You can put in many ingredients. You can do a lot of stuff, but you need data to validate it. So. I think those are the main take homes.
Yeah, yeah. I think there's Usman mentioned 2 categories of validation. Like you can directly compare measurements with model output. Then you can actually apply a model and, of course, look back after the recommendation has been implemented. If it works, probably the model has been right. But I think also, indeed, a third thing is very important in if you do comparative analysis. I mean, if with an unvalidated model, and then I'm coming back to this virus modeling, you can run different scenarios and look how the response behaves, and that's so valuable. Even if the data is not analytically correct. So yeah, people tend to always give the measurements right, and if something is lacking in the model, many people tend to shoot on the models very drastically, but not really questioning the plan A without the model. So David, what are your thoughts? You're really working at the other side. I mean, you are going deep.
Oh, thank you for inviting me on this conversation. I really appreciate that we are initiating a discussion on validation of CFD. That alone, it really, it's really, really good for me as a scientist, let's say. But as my 2 colleagues said before, I think the whole, point about validation, it's about how are we intending to use our model. I think that's kind of the key onto that. Well, let's say that would lead onto what is the level of validation that is required, or is it really needed in this case? So one way that scientists deal with a validation is to assign, okay, we know that we can determine, a certain variable, one single value, but that is actually might not be true. So sometimes we might need to, for example, include uncertainty in the process. And including uncertainty in the process would be, for example, one way to deal with validation, let's say, since we cannot, for example, say, or, expect that the system will just let's say from A to B, well, maybe it's between plus minus 1 of B, let's say. So including uncertainty will be key, I think, in CFD. But how to do it, I think that is really the challenge from a scientific perspective, let's say. But as as Usman said, and also Ingmar, depending on the objective of how do you use the model, you will require different levels of validation. So it's not the same, for example, the level of validation just of flowing water, maybe in large basins, which might not require like a lot of validation, because that's a process quite well understood. However, for example, the movement of different types of biological fluids, such as activated sludge or highly concentrated digested sludge, well, that's another issue, let's say. So I think depending on the system and depending, of course, on the scale, as Ingmar said, different things might be required, indeed. But at least it's nice that somebody is initiating, the discussion to trigger people. I think that's a good thing.
Yeah, it probably will allow to structurize this discussion, this framework that is now initiated in this paper, to first structurize it, and also not to throw away models directly, right?
Exactly.
So it's not black and white, huh? Not at all. There are a lot of shades of gray. Huh?
Yeah.
Exactly. I liked Wim. I liked your comment also on the data quality, and maybe I can shoot the ball back at David, because you have done quite some in-depth data collection, and that's also not a walk in the park, right?
Indeed, indeed. I think that would be probably, as you said before, probably the most difficult part on validating the model, because in CFD you can almost do everything. So it is the question if you can really access. So let's imagine that the CFD model can give you millions of probes simultaneously of information. How can you?
Yeah.
How are you able to extract that amount of information from the system sometimes? And there are even properties that you cannot even monitor. For example, because we don't have the current technology, or if we have the technology, it's very expensive. For example. So I guess that indeed scientists should devote, a lot of time to maybe work in synergy between experimental people and also modelers to really, design smart experiments so that later on can be used for model validation.
Yeah, this brings me to Daria. So Daria, you have actually started with a literature review. I think you have reviewed around 30 to 35 papers, which is quite an effort. Huh? Do you have a ballpark how many, in only in these 30 papers, how many different measurements or ways of showing data or ways to compare a simulation with the data have you encountered? How was the variety?
I don't exactly remember the numbers right now, so I will not maybe tell you specifically. But yeah, there were a couple of methods for validation. Most of them, in most of the papers there were few methods which were used, like few methods which kept repeating in all the papers. But yeah, in some of them also there was not really the results were not really validated, or they were validated due to some other papers, some literature, not really experimentally or on the small scale, for example.
Yeah, but am I correct that there is not really, that you didn't really find a structural way how people do things, and also that it's not often very objective driven?
Yes, I must also say at the moment when I was doing, this review, as you already mentioned in the beginning, that was during my internship. So it was very beginning of my work in the CFD sector, in CFD world. So I must say that especially at that time, finding some key or some scheme of those results or the validation of the way it was presented, it was not very straightforward to me at that point, especially.
Mm-hmm. Yeah. Mm-hmm. Yeah. What should now be the next steps? Huh? I don't know. It should be probably it would help if we come with a visual structure or so. I don't know. From the practitioner side, I always say to our customers, in 80% of our projects, we don't need any validation, or it can be even more than 80%. And then there are 20% left. But people don't at all. I'm talking from the practitioner side. People don't realize this, that it's.
I think an important thing here is the number of cases. I think in the past CFD is growing now to a certain extent and being applied more. So you will get more cases which are described with or without validation, but indeed have been successfully applied. And I think that is important. So if there are success stories out there, that's typically a leverage for further usage. So I think it's important. Another remark that I wanted to make is that maybe not only in the wastewater field, but looking also at process industry, where you might think that CFD is state of the art. It's not always the case, and you see that a lot of people are struggling with this and still use, for example, old methods based on RTD, for example, which is just assuming the thing is a black box. So I think bringing the message out there that there is something will probably also stimulate more the usage of or even the research on specific topics. And I think that on the one hand, the research that further confirms and further develops. But then at the other side, yeah, more applications, giving more confidence also in the industry. I think these are probably two things that will push things forward and should also be in interplay and say, okay, if something is maybe less less certain, or we see some more deviations, and then maybe it should go back to research to extend that a little bit and work or improve a little bit on that and reduce a little bit more the uncertainty.
So what now we have mainly talked about how far our models have they been validated in the past, how well established are the CFD models as like a choice of does it need validation or not. On the other hand, probably, and we have seen this, but I will now go to Usman. We can also talk about experience, and it means probably, if am I correct, Usman? If you're just starting a career in CFD, or you already have a decade of career in CFD, that makes a huge difference in your opinion on when should we validate or not. Am I correct?
No, that's true. Yeah, you're correct. Well, that's experience, of course. But first, I will just want to add to Ingmar's points. Like what should be the way forward? So one thing which what we've done in the past has been, so one thing is that you can devise new methods for measurements and data collection, data quality. And the other way is that you already look at what is available at the data and what you can do in the CFD to get to that data. So for example, in wastewater, we measure a lot of, we have a lot of sensor data. So there are like ammonia and oxygen nitrates, which are being measured all the time in the wastewater bioreactors. What we do in the CFD is normally hydrodynamics, which means we come up with velocities and at max multiphase fractions. But what we also do, what we did in the past was that we added actually another layer of complexity, which is that added a biokinetics, and then used biokinetics as a comparison or as a comparative tool, and then kind of validated through that. So instead of improving or going for velocity measurements in the bioreactor, we just updated our CFD code and then compared it. So it means that we were available with the whatever data we had already. So we didn't measure anything new, but we just updated our CFD code to match with the data. So this is another possibility, which can of course aid. Ingmar, you have something to say?
Yeah, I want to just give another example. So I think kinetics is one thing, but for example, I think when you model fouling of a membrane bioreactor, it's exactly the same. You also don't have the detailed measurement of where the fouling builds up, and I think then you use some kind of other measurements to see whether the observations are in line. And then sometimes I think it happens also the other way around, that basically a customer or an industrial partner has found something, has observed something, and then actually wants to use a CFD model to actually predict what they have observed. So I think we have an example there, but then making the true link between, for example, the shear rate at the surface of a membrane and the membrane fouling, that's another thing that probably would need more time to really develop, and I think people have been struggling with that for decades. So the question is, do you really need to figure that out up to the bottom? Whereas now you can already make huge leaps in for example, design of a system, or to already make an advancement. And I think that should not hamper. But it's another way, indeed. It's a very good point. It's another way of using data to not a direct measurement, but some kind of indirect measurement.
Yeah. And then coming back to your question, Wim, about experience. No, definitely that's very important. It has become very important, at least for us, because with experience of multiple and numerous validations, we have developed a very critical experience, which means that by just looking at the simulation results or the trends in the simulations, you can actually judge the quality of the outcome. And actually, with experience, is very valuable, because you can actually already foresee what are going to be the bottlenecks in your model, and what are the critical assumptions. And based on, by knowing that, you can already foresee to modify your approach either, or get some relevant data. For example, if you ask me, for example, in the USBs, so in the USBs, it's very important to know, what is the diameters of the granules, for example. What are the densities in there, and what is the fraction of the volume which is already taken up by the granules. So these are the important information you would need to put into your model. Even though you are not going to discretely model the granules, but still this has a huge impact on your model development and on your drag coefficients. So knowing these things, and what is the shape of the granules, for example, and just looking at them, what is the stickability, do they stick with each other? So all these things actually, and knowing it earlier will add into your assumptions, and then when the model finishes its modeling, then it becomes more reliable because it was based on some real data or some real information. So it's very important. I think experience brings a very valuable dimension to the modeling. And mesh, so we can talk about mesh like separate session, like how mesh can just the mesh, not the model, not the boundary conditions, but just the mesh can decide the quality of your results.
Yeah, so
and it has a huge impact.
How did you see this evolving, David? Building up experience.
Sorry?
How did you see yourself evolving and building up experience, and then looking how you do CFD now, or like ago?
Well, good question indeed. I'm not as experienced as Usman, but I can tell you that indeed it makes a huge difference if you have done something similar, the year ago or something, in order to be able to judge what is correct and what is not. So, in model selection, which approximations you want to use, but it also makes a huge difference on the time that you spend actually developing those models and actually offering, the simulations that you want to Ingmar in this case, or to in your case for another client. So the more experienced you are, drastically, you reduce the amount of time that you can deliver the CFD simulation. And I think this is really, really important, because this is not only something, reserved for the old people, that you need 2 PhDs in mathematics, 1 in computer science, etc., etc. Now everybody can do CFD up to a certain point, but of course, the more experience you have, the more knowledge you will put onto those models, and also the more confidence you will build, within the community also, but also with your client, I guess.
Yeah. Well, what I also find very interesting is if you invert the question. For example, not can we validate CFD and eventually then use CFD to do something valuable, but just make the question about validation obsolete. Can we let CFD do something that we simply cannot do in practice, right?
Yeah.
That is even not feasible. We have seen examples. So there are examples where things you can test them in CFD, but you can simply not measure or do these experiments in practice. Or CFD can do it better than if you would do it with measurements. Better, I mean, we can talk about tracer tests, for example. I think it has been demonstrated a lot. I mean, I will not generalize, but in certain systems that you can use a CFD simulation much better than a physical tracer test with measurement uncertainty, which costs a lot of money. Daria is working on a couple of projects. It's risk analysis related. People will not evoke these problems in reality. It is only the worst case if it's like a leakage of gases. Yeah, you will not test this in practice. CFD can do this. I don't know if you have other examples there, but if you ask me, validation or not, you have no other choice even in many cases. That's a bit.
Yeah, well, I think to build a bit further on that, one thing that I can think of is the virtual piloting is I think another example where you don't want to build all these pilots, and I think this is another thing that will develop. And the thing is, people have been doing that based on dimensionless numbers for many times, for many years. And I think now, yeah, this is just probably the dimensionless numbers 2.0, which will just, yeah, I think should replace this at some point. And maybe another comment that I wanted to make, because you said sometimes it's just impossible to measure, and that's something that I want to. So that's something that goes beyond CFD. So, for example, if you look at some literature of DEM or molecular modeling, that's even going one scale deeper, and there basically they have no way of validating. So they just say, okay, this is first principles. It should work. There's no way we should not validate it. It will always work. So that in that literature, this is vastly applied. So I think there will always be a boundary of what is possible and what is not possible. And I think, of course, yeah, the more you dive into the details and the more details you add, the more difficult it will become to generate data to even validate.
Yeah, interesting discussion. Yeah. Are there any additional thoughts of some of you? Things you want, take home messages, or something you would really like to share with the audience?
Yeah, but with respect to, again, from experience, you were, yeah, someone of you was mentioning about if you are a very new CFD modeler. The thing is that in the CFD you have so many different options. So you can actually play with your turbulence model. You can play with the coefficients in the turbulence models. You can play with your wall functions. You can play with your rheology models, multiphase models. There are a lot of models. So nested models, sub models, which means there's a lot of room for choices. So there's a lot of freedom to choose from. Which of course brings in also a lot of uncertainty, which model is suitable for what. And actually, to be honest, if you go back and read all the documentation for all these turbulence models, there's no one model for one particular application. You can actually use different models for the same application and somehow end up on the same outcome. But which one, that's not known. So that comes actually with experience, with reading a lot of literature regarding those applications and the models. So I think experience in that respect is very important in CFD. It's maybe not in other fields, but as much as in the CFD, because you can actually base decisions based on your experience, because you have so much degrees of freedom, and you have to really choose which one would work and which will not work. You already know which will not work, and yeah. So it's a bit of a it's a tricky thing. What I feel that you cannot hardlinely write a really rule like this model is gonna work for this and close. It's not gonna happen.
Yeah,
it doesn't happen.
Well, probably.
And then mesh. So if you combine it with models and the mesh, so some meshes are not compatible with a certain model, and vice versa. So so there's a lot of dimensions into it. I remember a project where we just did a little change in the geometry of the system. And then we had to change the whole turbulence model, because the previous turbulence model, which was working perfectly for that certain situation, it was not anymore applicable. You probably will remember the way it was a couple of years ago. So this can certainly happen. We had to change the mesh. We had to change all the turbulence model. Yeah, but this comes again with experience.
So if I'm correct, you actually need to build up a CFD experience in a certain domain, preferably, because then you become really good in this niche.
Yes.
Very, very difficult, or maybe impossible to be good at all of the CFD applications.
Yeah. We talk about multiphase. Multiphase is hugely wide. The applications we work are just a part of it, and there are so many other applications which are multiphase applications and turbulence applications. Yeah.
Yeah. And, well, I think this paper will hopefully initiate some further discussion, and well, we can also keep further building on it, like a good framework, further developing it. I think it needs a scheme, like a schematic, also. That we can vision. You have the application side and the fundamental side. The objectives are very different.
Another very good example Ingmar mentioned in the beginning. What was it? I forgot. It came in my mind and forgot. But anyways, so what I wanted to say was that you can actually model a certain system with RANs, two equation models. But you can model the same system with LES, which is much more accurate, which is much better, much more resolution is there in the length scales and turbulence scales. But why not use LES all the time? Actually, we have supercomputers now. Why not put everything on the supercomputer, do LES transient simulations, and get to the reality very quickly. The Ingmar's point was that models will be models. They will never be 100% reality. And then there is room for going towards the reality by using, for example, I just gave the example of RANs and using LES instead of RANs models. You will come closer to the reality. But the thing is, there are two problems. One problem is, how would you ever validate it? The more you go into the model, the harder it becomes to validate. Like you are doing LES modeling and then you are validating with a tracer test. This doesn't make sense. You can actually do RANs and still do a tracer test, and you can still validate. So the thing is that the more hardcore model you have, the more effort you need for validation. I think David can shed some light on that, to how are different methods which are much more complex and much more time consuming for the measurements. And then there are better models to compare them with.
It's probably separating out a submodel from the overall application model.
Yeah.
For example, if we validate a pilot installation or a full scale, we are not validating the turbulence model. We are validating the whole combination of CFD parameters and submodels.
Yes. And combination of models. Yes.
And I think what David worked on mainly was zooming in on a turbulence scale, if I'm correct.
Yeah, indeed. So that's actually very nice what Usman said, because it's always the combination of everything in the model which gives you the result. And if you have the indication, by measuring reality that was already correct, like the model, then you're actually validating everything as a whole, let's say. But as scientists, we see that we still have a lot of work to do to actually validate the models that describe correctly the physics, so that later on practitioners, and all the people that use CFD to conduct all these virtual reality experiments can really, feel confidence. I think that's really key. And I think it's a bit missing in the environmental engineering community, since we're lagging a little bit behind on physical characterization of the fluids that we work on, since they're really, really complex. And I think that's where really this paper is really nice, because it triggers already some, discussion on, well, how are we going to do this from the scientific point of view, so later on everybody can benefit.
Yeah.
Okay.
I like the analogy that you make when you mention LES. It's, let's say, to some extent in the direction of what I mentioned about DEM. There you model particles individually instead of modeling them as a different phase. It goes in the same direction. So I think there might also be an opportunity to use these models more and more, specifically on a smaller scale. I would not recommend to do LES on a huge lake. That would be would probably not be possible. But I think it helps to build confidence. So indeed, if you can do these models and it kind of confirms, and maybe they don't even need thorough validation, because they already go to a further or smaller scale to do. And yeah, I think it will probably point us in a direction where we have to put some more effort in maybe defining submodels. And I think what David mentioned with respect to rheology, I think is a very important one. And still to date, I think once you go away from Newtonian fluids, then basically you end up in empirical models. And I think there, for example, is definitely something that can be done. To some extent, you can use them, but I think that the additional knowledge that you would build would probably give you, would probably lead us to more insights, and maybe to come to completely disruptive reactor designs that we have never thought about in the past.
So Ingmar, I have one question for you. Are we losing the balance?
Well, I don't think so. I think we should. I think we should show to both the academic world and the industry that CFD is mature and it can be used. But we should just point to them that, like, okay, I think we made that example of who is even measuring the parabolic structure of a flow in a tube. Nobody, because this is just common knowledge, and I think this is how we should advance. And I think we should just for simpler systems we can say, okay, this is it completely makes sense and it works. So why should we invest a lot more time there? I think there are probably more challenging systems that would indeed need more. But I think it's just that finding that balance when you should go in depth and do a really thorough validation versus where you can be quite confident based on experience or based on a number of cases that have been described, that basically you should not do a very extensive validation. And I would say if something completely comes out of the model that would tell you that this is really far off from what we observe, then I think you should have the reflex to probably go back, but you will have that anyway. So I think there it's I think it's a matter of finding that balance, and I think probably up to us to demonstrate in the different fields where that balance really is.
Yeah, food for thought. The good news is we are all busy. We keep ourselves busy. And we can apply the models, so we can do research. So a lot of challenges ahead. We will not get bored. And the benefit is, even in such crisis where everybody works from home now, you can still do fast CFD simulations. That's also very good news. So one question left for Daria. So Daria, how does it feel to be in the Hall of Fame of scientific publishing officially?
When I started this research, started reading this article, I had no clue that it will end up as a scientific article. And actually, I've never been thinking that I will be co-author of any. So it's pretty new situation. But I think it's a good feeling. It's a very nice feeling that the work you've done, actually someone found it very useful, someone found it interesting, and someone made it very good topic out of that. And it's like the idea of this research ended up as a good article, and now we have opportunity to discuss that. So that's very, very nice.
Great.
I like what you say, Daria, because I think, I mean, we just took a helicopter view here and put a lot of things together, and I think that kind of triggered the interest of people to look at things from a broader perspective, rather than because what you typically see in scientific publishing is like, you do research, you submit it, and then people are going and digging into the details. Whereas it's always good to also zoom out and have a look at, okay, how does this now work? And the fact that people are interested in it is probably because they have asked themselves this question and never really came to thinking about it because they were mostly lost in details.
Well, that's with this paper we kind of visualize the whole pipeline, from fundamental research to application of CFD, and everybody working on CFD somewhere. And then okay, I'm here, this guy is here, and we have actually different objectives, different challenges.
Yeah.
Correct.
Yeah, great. Well, yeah, I think I'm very proud to be co-authors the paper with you. Yeah, it was an honor to push this forward.
Yeah.
So thanks everybody for the discussion.
Yeah. Thanks for organizing it, Wim, and being persistent to still organize it.